lot, and thanks everybody for inviting me here. Quite excited to present again. And I mentioned earlier, for the ones who just joined, I'm a bit nervous because this is my first online talk in over a year. And before that, I was nervous to get back to on stage talks. So let's see. So I'm going to talk about what recently I've discovered could be labeled as Neuro-Symbolic AI. And we're focusing on decision-making under uncertainty. What you see hopefully moving there is some simulation of drones moving through some crowded environments under a lot of uncertainty, for instance, wind conditions. So let us see where we go with this. So let's be very quick with the general motivation. So we all know that AI systems have a great potential already entering our society, our everyday work. Think about the unavoidable autonomous cars, some delivery drones, factory robots. AI has been used in the stock market. I mean, then there's these shiny examples like the Mars rover and AlphaGo. I think you all know these examples. So when I was doing this motivation, I thought at some point, let's make this a bit down to earth. So there's been quite a push in the last years for people whose research is centered in something called informal methods or formal verification in my case, to kind of marry this with the bigger area of AI. And the promise of this marriage has always been that we can give some formal guarantees on AI system behavior. We have structured semantics. We are using very nice, well-defined models. We have formal specifications. We are talking about scalability of AI systems, and some word that has been quite prominent that we are looking into the safety of AI systems. And well, I've been trying to talk about this marriage of two areas for quite some time, and there have been a lot of events around this, and some of them are organized, and I'm not listing ones I didn't organize. I still attended. There was some in the Netherlands, some Lawrence Center workshop where also Jana was involved. There was some workshops at conferences. There was some Dutch seminars, and upcoming, by the way, this advertisement are two Dutch seminars. One of them organized together with Jana, which are always trying to bring together some areas and see what are the strengths between those different disciplines. And while these discussions, I sometimes get the impressions that it's not really a marriage between two areas, but it's rather that one area is kind of proposing to the other area, right? So because if we follow methods, people say something like we give guarantees, then AI people would ask, well, what is a guarantee, or how do we get your models that you're using? What are specifications that are very meaningful that can really help us in our AI, or perhaps extended our embodied AI or robotic systems? How scalable are your methods? And what has been bugging me quite a bit, what actually is safety? So what is safety? We'll get back to this. So let us try to jump a bit into what we're trying to do. So one aspect of bringing together this area of formal methods and AI is that we might be doing some learning from some real system. And from this, we obtain a model somehow. This model, then formal methods people would say we can just verify this, and then perhaps we want to get back to the learning part here. And I've, as I said, I've recently learned that there's a word for putting such structure in a learning process, which you could cover under a Neuro-Symbolic AI, which integrates neural and symbolic AI architectures, where here, and I'll get back to this in detail, our verification part of formal modeling is the symbolic AI. Perhaps a bit more far-fetched, as I've also learned that if you have such a setting where you really derive a system from data and then give some guarantees on its behavior, could be framed as a digital twin. If you kind of learn from a real physical system and you learn a model, then this is nothing else than a digital representation of an intended or actual real-world physical product, system, or process. So this is two ways of capturing this whole loop of learning a physical system and then I don't know, perhaps providing some behavioral guarantees on the system. Okay, now I'm back to this topic of safety. But when people hear safety, they usually would think that safety means nothing very bad should happen. So for instance, the delivery drone should not crash into some buildings. The autonomous car should not crash into any pedestrian. And my favorite example in space, there are some satellites flying around, and they should not crash into other objects in space. So what we really want is that our AI systems are secure, resilient, they are safe. There should be some fallback plans, and this is something that has been stated all over the world in many agencies, many position papers. and other and other areas. So I've been thinking quite a bit, what does safety really mean? And it's not really clear. So safety could mean that we want our systems to be robust. It could be dependable, want to certify that it behaves in a certain way. We want it to be correct. We also want it to be reliable. So what I think, what is the most, say, overarching description that we can give is we want our AI system to behave as we intended to. Yeah. So this is something where I can live with. We have our AI system. This can be a method. This can be a robot. This can be anything. We have some ideas how it should behave, and we want it to behave as we want it to. Yeah. So this is our general setting here. And let's now make this a bit more concrete. So here's a short overview. So we'll first talk a bit what is actually decision-making under uncertainty, at best intelligent decision-making. Then we'll talk a bit our research plans, vision, and highlights. I will talk a tiny bit about teaching our group, and then I will try to wrap it up. Okay, we start with decision-making under uncertainty. And our approach to this decision-making uncertainty is actually Neuro-Symbolic AI approach, where we integrate these Neuro-Symbolic AI architectures. And what we really try to do is to address complementary strengths and weaknesses. We don't try to do something like, you have a neural network, do some verification, but really try to close a loop here. This is something that is very central in our research line. And more concretely, let's get back to this part where we learn a model and then want to verify it. But then from this result, where we do some verification or learn something about this model in the sense of that we can give any guarantee, we want to bring them back to the learning part. So how do we want to do this? We tap into several research areas, and a bit broader, let's say we're working in formal methods and AI, but also we're taking approaches from control theory and robotics. And more concretely, we're looking into rigorous model-based verification, decision-making and uncertainty. At some point, we will want to work in more realistic systems in continuous spaces. So there we need approaches from control theory, and from robotics, we draw inspiration and we try to get some interesting case studies. So now the question is, what these are four kind of isolated fields, so it brings them together. It's really the idea that we have to reason about uncertainty. So what we actually want to do is, in the open, in the real world, there is a lot of uncertainty, and we want to be robust against this uncertainty or reduce it in order to be robust against it. And some bit more concrete theme on how we're trying to do this is, let's say we have some partial understanding of a system. We could capture this partial understanding in a partial model. And this one we can verify. And verify for us means that we can, for instance, say with, let's say, some high confidence with upper bound on a certain probability, we can be sure that something will behave as we intend. This information might not be enough. Then we need to learn more about the system. So we do another learning round, and then we might update our model. And then again, we can compute, let's say specifically, the maximal probability to crash, right? And if this is too high, then we need to learn more or change something. Yeah. And what is important for us, that this whole, what I call verification as a backbone, has concepts like control-based abstractions that uses robust optimization techniques. What we really try to do is to have tightly integrated verification and learning methods that, as I mentioned before, are robust against uncertainty under this our high goal real-world conditions. So we want to really work in the open world, or we will want to lay the foundations to work in the open world. Let us move to a very simple example. This is a bit toyish and conceptual. So look at the setting. You have, I guess, all seen all these simple grid world examples that people use. So here we have a delivery drone, and it wants to deliver some packages to some of the buildings. And after each delivery, it wants to return to its halting pad. And while it is moving, it is a very crowded environment. It doesn't want to crash into any building. It shouldn't be blown away by some wind gusts, and it should also not crash into some other objects that are flying around. Yeah, and I mean, from these factors that I mentioned, you can see that there is a lot of uncertainty, which could be caused by a sense of imprecision of this drone. It could be subject to wind gusts, and it could have a very limited view in these crowded or also called contested environments. And this means that we have a rather complex task specification, which is, if we want to read it out, almost surely we want to always return to the halting pad after a delivery, and the crash can only occur with a probability at most 0.001%. earlier I had 0.1%, but then I got the feedback that this is too high, so just use this number. And what you see in gray is the specification in temporal logic. And I will have some slides where we have these gray mathematical descriptions of what I'm saying. And if you have questions, please interrupt me. For now, these are just stated there to show you that this is actually possible to capture this in the formal way. So what we are asking ourselves, what are the challenges if we want to provide guarantees on the behavior of an agent under such factors in the uncertainty? So the more scientific challenges that we want to talk about are that we want to make our methods scalable for realistic applications that have, let's say, high-dimensional feature spaces. Yeah, so we have factors like wind, altitude, temperature, and very large environments. So it can be a lot of things. So what you see in these drawings are moving from a simple grid world to a continuous space, to a gridded 3D space, to a continuous 3D space. You can see how these problems really grow in complexity. So this brings us to other challenges that we work about, which are continuous state action spaces, uncertainty, partial information, and then these are all things that have been considered in some way, but now we want to work with this in real data-driven problems, right? So we have some knowledge about our system, but we don't know everything. And then data might come in. We might learn new information while we're operating these systems. And this is our real challenge to bring this all together here. Let's make this a bit more concrete. So there's this technique of reinforcement learning, which is a typical kind of machine learning technique that works in uncertain environments. So what does RL, reinforcement learning, do? It, in some way, brute force explores its environment by taking certain actions and observing the feedback signals that it observes. Then, in a very episodic way, it determines the optimal way to make decisions. The episodic is important because reinforcement learning really does one episode, try everything out, then there's some halting criterion. It could be in the simulation, it crashes, and then it starts again, another episode, and on and on and on. And then there are convergence guarantees that up to infinity, we will converge to the optimal plan within this uncertain environment. And very clear limitations of reinforcement learning, despite all the success stories that we have, is that exploration is very obviously safety critical. So we cannot just put a reinforcement learning agent on a robot and let's just try everything out. It might just crash. Reinforcement learning is also practically sometimes hard to use because it is extremely data hungry. In order to converge, needs to sometimes use millions and millions of episodes, and then it depends a lot on the tuning of your external hyperparameters to get to good results. And for us, also very interesting is that reinforcement learning with the typical reward-based setting cannot capture more sophisticated task specifications like the one we have seen in the beginning with this temporal logic constraints about the delivery drone. Yeah. Okay. Then kind of dual to reinforcement learning is kind of big family of formal verification techniques, sometimes subsumed under the term model checking. So what is this? We have some model of environment and we want to prove that this model is correct regarding some formal specification. For these models with uncertainty, there are rigorous numerical techniques, and the models that we use are, for instance, Markov decision processes, MDPs, with various extensions that concern the type of uncertainty that we have. Partial observability, you might have adversaries moving to game-based settings. So this conceptually sounds very nice, but there are also here big limitations, which are the richer the model becomes, the harder the underlying problem is, both theoretically and practically, which also means that we have a big scalability problem to reward scenarios. If we have billions and billions of states, it simply won't be feasible anymore. For me, kind of an overall problem is also often that it's not even clear how we can get a model. So is there a model that faithfully gives us the system that we need? And again, it's often unclear how to integrate this, perhaps in a continuous way, with the data-driven problems that we are facing in the real world. Yeah, so we have reinforcement learning, we have formal verification, and this brings us to our real research objective, which is to really elevate the state of the art in safe and correct or dependable or reliable decision-making for AI systems. And for this, we want to develop more scalable and data-driven verification techniques that integrate with the data-driven reinforcement learning. And there are a lot of challenges that we want to actually address, as I mentioned before. Okay, so these are overall research picture. let us move to some more concrete challenges and highlights that we're working with. So I've said before that we really want to bring together some areas, formal methods, AI and others. And there has been some progress in our group over the last years. And we've been working on the kind of 3 cornerstones that we want to work with systems that deal with uncertainty and partial information, want to work on continuous spaces, and we want to make reinforcement learning safe. And what you see here is a list of publications that we had over the last years, which are color-coded with the areas that we have there. So it was, for us, a big challenge to actually be able to get our results into the different communities. This, I think, has paid off because by being able to jump into different fields, you also learn a lot of the understanding in the different problems that you have. Okay, let us start with some results and some challenges in uncertainty and partial information. So as I mentioned before, for me, a big challenge is that we want to somehow obtain a model that is dealing with uncertainty. And this is also identified as a big challenge to combine data-driven learning with model-based reasoning. So let's say for us, we concretely want to learn and also analyze a model. We want to learn this from data by obtaining data of a system. The model should robustly capture all uncertainty and perhaps probabilities in our system. We need to be able to account for changes in the environment, right? Because it can change, or there may be parts that we haven't observed yet. And it should be also amenable to efficient model-based analysis. So we don't just want to learn a big model that nobody can analyze. We want to keep in mind that we will need to do something with this model. Yeah. And there's been some progress on this, and which is by far not done, but this is our first approach. So in these Markov decision processes, they are used in AI, formal methods, and also in robotics quite a bit. The big problem is that these models, if they are derived from data, you easily run into statistical errors. You might also have, as I mentioned, changing environments. So it means that the model that you currently have might not faithfully capture what is happening. And based on these problems that you might have, if you base your plan on this model, you might have very unsafe decisions. So what we actually went out to do is we want to learn these uncertainty models with intervals of probabilities or bigger uncertainty sets of probabilities to capture really the deviation that could happen from a point estimate of a probability. So this should account more robustly for statistical errors in our system, should be able to adapt to new data in case we have an environmental or distributional change or shift. And this is important for us, at any time, we should be able to compute what we call a robust policy. So what does this mean? Let's say we have learned a partial model so far, which is captured by big uncertainty sets, big intervals. So then what we can do is we can compute a policy that in a very pessimistic way gives us a plan accounting for all the uncertainty. So under the worst case instantiation of our uncertainty, we can give you the following guarantees. Yeah. So let's say we have this prior approximate MDP, then we use reinforcement learning to collect more data with some optimism in the face of uncertainty concept. I can explain more about this. We use this data to update our intervals. We compute at any time our robust policy. And then if this is not enough, we can again collect data. So this is a very general scheme. Let's make this a bit more concrete. So in the very usual setting that if you are working in a related field, you might think about is that you use some probably approximately correct learning, which is in the end, you have a point estimate of a probability with some error margin around it. Yeah, so these are confidence intervals essentially. For PEC learning, you can give a correctness guarantee that this uncertainty model actually captures your environment with high confidence, but usually these intervals are very, very conservative and the setting is very data hungry. You need a lot of data to give any guarantees on the confidence on your model. And it's usually not adaptive, right? So once you converge to an interval, you can only shrink it. This is the very easy intuition. So what we developed was an approach that we call linearly updating of intervals, which is a Bayesian interval update. And here we update not a point with a margin around it, but both interval bounds in a separate way. Yeah, and this does easily account for prior data conflict, which means we have a lot of data incoming. We estimate our intervals, and now something is happening that doesn't fit with the current estimate of the intervals. And then in this Bayesian scheme that we employ, it's very easy to enlarge these intervals and then shrink them again. And there's certain hyperparameters, for instance, how important your prior information is to kind of a slide a window approach that you take perhaps the last 10 steps more importantly into account, but this is all a matter of tuning. Yeah, so this is a very general concept. And what we see in our experiments is that this approach, what we call LUI, is very effective to find optimal policies faster than other approaches like this point estimation, pack learning, or optimism in the face of uncertainty. No details needed here. It's just what I want to say is that we can often find a robust policy quicker as finding the optimal policy based on other approaches. For me, always more important was the fact that we can be adaptive to changes in the environment. And we can see this here. So now we want to minimize, we're going down. And what you see is that the blue line, if you can see the colors here, is moving to some optimal value. And then we see this big spike, we change our environment. We just change the MDP from which we are generating data. Then we see that the performance of our approach really drops by going up, but then quickly recovers from this and goes down to the optimal value. While all the other approaches inherent to their algorithmic nature cannot recover from this change in environment, right? So this was our, I think, key contribution of this learning approach, that we can really learn models that are robust against changes in our environment, in our distributions. If you're interested, there's some literature for this. This is a Europe's paper from last year, which we called Robust Anytime Learning of Markov Decision Processes. Okay. To speak about another challenge, which is, which people have told me often the holy grail in neural network controllers, that you want the controls to be robust against many potential environments that you could be working in. So our approach is that we say we might have a big family of models that capture potential changes in the environment. And this family, from this family, we could select some samples and then train our neural network. And then if we're able to analyze the neural network in some formal way, we could use this analysis to say, well, this is now robust against the whole family or not. If it's not, we should get some data to update our neural network and retrain it. So this is our very, very general scheme. Let's go about to this and to some specific approach that we are employing. So some years back, there was this big hype starting about neural network, robust neural network verification. And I tried to understand it better. At some point, I felt that many very strong groups have been working on this. And to me, this problem was always very hard to understand and hard to understand what you can actually do. So I'm not really doing neural network verification. At the same time, I was working on finding policies for partially observable Markov decision processes, which are very hard models to analyze. So these are also very hard problems. Then at some point, we kind of understood that, well, sure, both problems are very hard, but neural networks are used as very efficient and effective policy representations for these POMDP models. So our thinking back then was to try to bring these two worlds together. And this is what we try to do. So the overall idea is you have a neural network, you have a complicated environment, you might have a model that you cannot really analyze, and then try to assess the kind of performance of the neural network policy in the actual environment it's operating in. So this is the very, very general idea. Let's make this a bit more concrete. Let's say we have a POMDP model, and we have some formal specification about, let's say, safety. Then, so what we have now is our neural network policy for this POMDP setting. We want to verify, right? We want to know, yeah, this is performing well or not. So what we need for this are a few requirements. We need some suitable neural network architecture that can work in these environments. And we want to kind of close the loop. We want to be able to, if the answer is no, to improve the level of training of our neural network. I'm a bit careful with the next point because it says towards understandable decision-making. I don't want to claim that the policies, controllers, whatever you want to call it, are very understandable. It's just that we take one step away from the rather hard to understand neural network controllers that we have. And what is perhaps more important, that the policies that we get are easy to verify. So how do we do this? Let's take some formal step. We use as our controllers so-called finite state controllers. You could also call them finite state policies. So what are those? These are basically input-output automata. Some people might know Moore machines. This is a randomized Moore machine because it gets as input an observation from the environment, and based on the observation, outputs a distribution over potential actions to take based on this observation. So it could, the observation could be the obstacle is very near, so then it returns a distribution over run away or please approach the opponent, the obstacle. So it should be a very high probability for running away in some sense. Yeah. What's nice about these finite state controllers is that these are formal models, well defined, and you can put them together with for instance, a POMDP model that you have and flatten the space and essentially encode the whole memory-based decision making into your model. Of course, at the cost of blowing up the state space, but if the size of the controllers are somehow restricted, if you are able to restrict the size of your controllers and still maintain some quality, then you can use it as a very nice kind of integrative method to compute the controllers. Okay, let us see how we use those. I come back to the setting where we have our POMDP model and we have our specification. And with some neural network controllers. So what are we going to do with this? We use a so-called generating policy, which is nothing else than, for instance, a reinforcement learning agent that explores your environment. So this generates data. And then what we do is we train a recurrent neural network. We use a recurrent neural network with a LSTM architecture to account for sequential decision making, because the path is important in these models. Yeah. So we somehow train a neural network. This is the standard approach. You find a clever way of training a neural network, and then you want to know how it performs. So what we actually do is we use some existing methods to extract from this recurrent neural network, a finite state controller. And then we do something that is really putting the finite state controller on the model, computing the product that I mentioned before. So we have now encoded all the memory-based decisions into our model. And what we get then is actually a very simple, purely probabilistic model. It's a Markov chain for which this verifying the specification is a thing that can be done for billions of states. So the answer that we can get now, based on the extracted control that we have, the answer of satisfying our spec is yes or no. Okay. This is the first step. And as I said before, we want to make this kind of neuro-symbolic in the sense that we use the strengths of all words. So we want to close the loop here. But how do we do this? If we analyze our model, we get a lot of information that we might so far not be using. For instance, it could be that we can easily find out what choices that we made are very bad for satisfying our spec. So this means, for instance, which actions have a very, very high probability of violating our specification. So we use this to change the policy to generate data and then generate new data and retrain the network. And then we can loop again and perhaps at some point get to the point where everything is fine and we have satisfied our spec for the extracted controller. However, there is some slight problem in here. So while we do the extraction of the finite state controller, we need to fix a memory bound, meaning the number of states in the finite state controller. Yeah, and it could be, say, 10. And now the argument can easily be, well, 10 was not enough to capture the recurrent neural network behavior precisely. So we want to also get an indication where we need to increase the precision of the finite state controller or retrain the network. So these are two different things that we can do to improve. So what was our simple thinking here? We use some information theory measure, which is the entropy. And the idea is if we have a very low entropy in our decision making, which could, for instance, mean that we very clearly pick a certain action, then the neural network seems to make rather informed, well-trained decisions. And then we increase the precision of our finite state controller. The alternative is that it makes highly random decisions. There's a lot of randomness in our decision making. We measure this with a high entropy, and then we retrain our network. So this was our simple heuristic to decide, do we need to retrain or do we need to make our extraction more precise? So in the training procedure, what we see here is this very quickly, what you see with the dotted curves that should always go up. This is the actual probability to satisfy our specifications, and the crosses means this indicates the number of very critical decisions that we are making. Yeah, so in the left one, you see this is very nice, everything works as we intend. In the other examples, it's a bit more tricky, and this indicates the following. This is the heuristic, we never know how it really performs. The other question that people could ask is, does this now scale? And actually it does. just very quickly, we can scale this up to millions of states in our POMDP models, which is far beyond reach for state-of-the-art POMDP solving methods at the cost of not being guaranteed to converge to an optimal policy, of course. So the thing that we can do here is show empirically that this behaves well. Well, if you're interested in this line of research, there are a few papers, and the most recent one is actually this from last year in the Journal of AI Research, where we kind of subsume our approaches to extracting these finite state controllers in a data-driven way. Okay, I've talked about these in certain systems. Let's now talk about continuous spaces. So what we do here is the following. Say we have this problem. We want to move away from these grid-based scenarios where we say, hey, jump from this cell to this cell, and to this cell to this cell, and then you're fine. Because I mean, while you are just jumping, you're actually moving in continuous space, and this is clearly also safety critical. So a very general approach to deal with such problems is some data-driven verification and abstraction method. And this is our challenge here. So we have our potentially continuous system environment, and of this, we want to construct an abstraction that is, again, easy or good to verify, some finite state abstraction, but that has a clear performance guarantee between the abstract model and the continuous space. Yeah, for instance, you could, again, give probably approximately correct pack guarantees for the relation between the abstraction and the continuous model. Yeah, and we also want to use this abstraction potential to reduce dimensionality of our problem. So with this very general setting in mind, let's look at an example, and we call this, because this is called the Fly High seminar, let's fly an autonomous drone in a safe or dependable way. So we have our drone here. It wants to go to the green read space and it should avoid some obstacles in there. So far we have a certain mass of the drone and we have a certain wind altitude. So based on this, we want to compute a feedback controller that, based on the current state, returns an action to take. So this is a good plan. Yeah, so this is a good plan given the current setting that we have. But now let's say we can't really capture the wind speed, so it could be very high or very low. So there's already some uncertainty in there that we need a different plan if we have a very high wind speed at some point. Yeah, let's make this more complicated. Let's say we are not very sure what is the mass of our drone, because this is some configurable system and we do not know how it is configured. Yeah, so if the mass of the drone is uncertain, then the actual outcome of a plan is variable. It could go to several states, to these boxes that you see here. Yeah? So these are different types of uncertainty that we deal with. And what we have is the stochastic wind conditions. We could frame them as so-called aleatoric uncertainty, which leads to probability distributions over the outcome of certain actions. And as the mass is unknown within some bounds, we have what we could call epistemic uncertainty, where the actions have some non-deterministic outcomes depending on the mass that we might actually have. Yeah, so we have aleatoric and epistemic uncertainty here. Let us look into this with a bit more detail. So in the stochastic uncertainty, we have some variability due to this random effects, and each outcome has a very certain likelihood. Yeah, so it is uncertain, but it's a certain likelihood of something happening, and it cannot be reduced by gathering more data. It's just given. With the epistemic uncertainty, which is also called systematic uncertainty, this is due to a lack of knowledge. We don't have any likelihoods attached. It could, in theory, be reduced by gathering more data, so we could learn what is the actual mass of our system. Now, the big question is how to design a control that is safe despite these different types of uncertainties. So our general scheme to deal with these problems is to first create a finite state abstraction. Then this abstraction actually is a Markov decision process with certain intervals, uncertainty sets that come from the aleatoric uncertainty that also captures the epistemic uncertainty. If we have these models, we can, I call it here model checking, where we can use existing off-the-shelf very efficient tools like the Prism model checker to compute these robust policies against uncertainty. And then we give formal guarantees that the policy that we compute here actually maps to a controller of a continuous space that performs at least as well as the policy that we computed on the abstraction. So how do we do this technically? Let's say we have a certain action of moving from a certain state to another state. Yeah. the outcome is random. So what we want to know, what is the probability of reaching a successor state via some action? So what we do now do is we use some sampling techniques if we have access to a simulator that gives us these confidence values on probability intervals. And then if we collect enough samples, then we can actually compute these intervals of probability. So again, a bit more formally, what we can do now is we use a sampling approach that is called the scenario approach. And then we can give easily and with rather high data efficiency, giving a guarantee based on a user-specified confidence probability that the interval is, let me phrase this differently. What we can do at some point is say, if we draw another sample, then the probability that the sample will be outside this box that we computed is at most beta, right? So this is our confidence probability. So this is what we do with aleatoric uncertainty. So what do we do with this epistemic uncertainty? It's the following. So again, the setting where we take a certain action and then at a certain point, depending on like an average mass. So we change this, we make this minimal, this is a different outcome. We make this maximal, yet another outcome. Yeah. So what we need now is we need a robustness against any realization of this uncertainty. We capture this with these boxes. Yeah. So these boxes are kind of conservative bound on being robust against this uncertainty. So to summarize this line of research is we want to control autonomous systems. And by the way, technically, we can use any form of noise that can be even non-Gaussian based on an approach called scenario optimization. And we result in a robust policy that guarantees that the system will, with high confidence, satisfy our spec with, for instance, more than 90% probability. What you see moving at the lower right lower corner is with high uncertainty in our system. If we simulate this many times, then you see different flights of the drones because they have to capture about the uncertainty. So this introduces more randomness in our policy. And with low uncertainty, we're actually able to go through this little hole and find a more efficient plan. But I mean, what we can do here is, given the uncertainty in our system, we can compute your plan and measure its performance. If you're interested, again, there's literature. So there's some AAAI papers and some JAIR paper. And I always at this point want to give credit to my PhD student, Tom Bardings, who won the AAAI 22 Distinguished Paper Award for one of these works. So check it out. It's, I think, very good work, and feel free to reach out to us if you're in some form interested. Let us now move to the last part, which is safe reinforcement learning. This is a rather critical field because I think 5 years ago, there were barely any works on this, some papers that took some specific settings. If you check on DBLP, nowadays this has increased like crazy. So I think last year there were like 500 papers that had some form of the title safe reinforcement learning in there. So we need to be very specific with the actual problem that we're dealing with. So what we try to do is we want to ensure some correctness, right? So of our exploration in the RL agent. So what we do is we impose, we have our reinforcement learning agent that takes an action in the environment. And what we do is we know something about the environment based on some partial model. We impose something that people traditionally call a shield that blocks certain actions that have too high probability to bring us into a critical state. Somehow this shield is perhaps a bit too restricted to the safety aspect. So what it actually should be saying is we know something about our system and we avoid certain actions that are either safety critical or we don't actually need to satisfy our specifications. So what shield really does so improves also the convergence rate of reinforcement learning. So in some form, it's an elegant way to inject domain knowledge in our reinforcement learning system. And what we usually want to do is want to integrate a verifier in our system that can continuously, based on a model that we also continuously update our mechanism, our shield, to block certain actions that are either unsafe or irrelevant for our specification that we have. Okay, that was a bit fast, but I hope this is fine at this point. So let us see what is the state of the art. What we do is we use the following setting. We have our OpenAI gym environment for some reinforcement learning task, and it does train a state-of-the-art reinforcement learning agent in the form of some neural network or some other entity. And we connect this to a model checker from a verification tool called Storm. And so what we can do with this is the following. We can really say, hey, we have a neural network controller. Now apply it to a formal model that we have, right? And then also train the neural network controller based on this model. We tried this out with a lot of different RNN agents, and you see the overall scheme in here. So let's see how this works. We're going to a simple grid world environment here. So this is tuned reinforcement learning with the reinforce agent. Before I start the video, let me quickly explain. So what we want to do here is the blue dot in the upper left corner wants to go to the green corner in the lower right corner, right? It only sees a certain range, and it needs to avoid this other dot, this pink dot, if you see the colors here, which will be moving. There's a safe zone above the dotted line. And as I said, it cannot concretely estimate the position of the, see the position of the moving obstacle, but it needs to estimate it from data from observing what happens. Okay, let's move this. So what is happening here is that if we just train a reinforcement learning agent for many, many times with a lot of tuning, it will never converge to a solution where it can safely go to the green area. In the shielded case, it can. Now the question might be about this. Well, that's kind of cheated because you knew your model, you knew what was happening. Well, we assume only very minimal assumptions here. What we do assume is that we do know kind of the potential movements of the obstacle, but not any dynamics, any probability. Yeah, and from this we can create a shield that almost surely will safely reach the safe area here. Yeah, so if you're interested in this kind of safe reinforcement learning work, you can check out some papers. I've listed only 2 here. The latest one was safe reinforcement learning via shielding for POM-DPs, which is being published at AAAI this year. And there's some more theoretical groundwork published at CAF last year. So I'm Ayana, do I need to hurry? See you. But I'm also near to wrapping 15. Up, so let me.
Yeah, you have 15 minutes, including questions from now. So.
Okay, including. So I'll be in a few minutes, I will be done. So let's see. So this was the kind of progress I wanted to tell you about. We have been doing several approaches on uncertainty, continuous spaces, and safe reinforcement learning. And now I will answer some questions that I usually get. So the first one is the following. We talk about these guarantees all the time. So the question is, what kind of guarantees can we give? I mean, it, of course, differs a lot on the assumptions that we make. But something that is especially inherent to these approaches on finite state abstractions is the following. We have some, say, system environment, which could also be seen as a dynamical system with some noise, perhaps with unknown distributions. For these very hard to analyze models, we get a PEC guarantee that the model that we actually compute is correct, right? So we have a high confidence that this model is capturing the continuous, very complicated system they have. Yeah. Then on this, and this has been a question from AI people. If we have this model with uncertainty, we don't do what AI people call approximate inference. We do exact inference, because what we can do with these bounded uncertainty bounded models is we can really compute exact upper and lower bounds on certain probabilities. So this is exact inference, which means we don't add another PEC or confidence guarantee here, which means in the end that we get PEC guarantees or approximative guarantees on the actual system behavior. So this is a guarantee that we can give if we can do any approximative guarantee on the model that we're using, then we can be exact from this point on. Yeah? So this is, I explain this because I want to make sure that nobody thinks that we're propagating certain confidence problems here. We are not. Really just putting our confidence guarantee on the model, and from that on we are exact. Okay, so if we have this, next model that could be asked is, well, you always talk about your models and a guarantee, so how hard is it to actually check anything here? Well, with these, let's say we start with the POM-DP models, and we have some quantitative specs where we say the probability to reach some critical status needs to be above or below a certain threshold. Then to get optimal results, the underlying problem is undecidable, but there are very efficient approximate solvers or sampling-based methods here. If, however, we restrict our policies to finite memory, like with the finite state controllers that I mentioned, then the problem is only NP hard. It's rather okay to compute such a policy with then exact guarantees. Yeah. Well, for a specific problem with our almost sure properties that I only mentioned it briefly in the shielding setting. The other problem is extra time complete, and they're rather efficient satisfiability solving solutions to these problems. Yeah, so this is kind of the setting. I can explain more if you're interested. How do we implement our work? I mentioned this before quickly. So what we really want to do is to have a tight integration of tools from the machine learning AI area and formal verification. So what we need is we have a model simulator to train reinforcement learning policies. We have a callback to apply a neural network to a formal model. We can easily integrate further tools if we want. Of course, these tools are public access and are rather well maintained because we're using them quite a bit in our group. So if you're ever interested in our tools, one of them is called PoolMC, a comprehensive tool for reinforcement learning and model checking. Please contact us or check it out. We're very, very happy to help. I said I want to talk about teaching. This will be fast. Why is this interesting? Well, because we've been able to identify a lot of very nice especially master projects in the past that many of them have been published actually that are going into all these directions. So and some fun example, this is actually bachelor thesis, the following. So let's say we want to learn from human data. What happened here? I had a student who loved to play Pac-Man. So what she did was she let all her friends play Pac-Man again and again and collected all kinds of data from how these humans performed. And then evaluated this data creating a formal model and then verifying it, and then extracted an AI for Pac-Man that played much, much better than I could ever have hoped for. There's another game that is rather addictive, which perhaps you know, this 2048 game. I wasted a lot of time on this, especially during my PhD. There was a student who wanted to reinforcement learning, but was extremely frustrated with RL's performance. So the student included a lot of side information. To train it better. Then at some point the student came to me and was basically saying he fails his bachelor thesis because they cannot converge to an optimal policy. Well, if you just use a random agent, it doesn't converge to anything. If you put in some knowledge, you at least get to a higher score. So this was actually very nice, I think. Let's wrap up. This is my group. I want to give credits because all of them have been involved in the results that I've been presenting. So there's my postdoc, Tiago Simão, who has been co-supervising several of the PhD students that I am supervising. Some of them just started this month. And I want to mention two master students because they are employed as so-called Alice Excellence Fellows. And both of them have, as part basically of their master thesis, already published a paper in our group. So I was very happy about this. And yeah, big thanks to all of them. Advertisement, as Jana mentioned, we have this ERC starting grant in our group, which is called Data-Driven Verification and Learning Under Uncertainty. If any of you is interested in one of those topics or know somebody who's interested, we are hiring. I'm especially looking for postdocs, and this research is roughly in line with what I told about here. So let's really wrap up now. We're working on tightly integrated and novel learning verification methods. We want to elevate the start both in formal verification and also safe reinforcement learning. And everything nowadays needs to stop with a vision. So our vision is that we want to help developing data-driven systems so that decisions are known to be, and now I would need the other slide again, correct, safe, dependable, reliable, whatever you want to put here, right? So we want to get some understanding of system behavior. Yeah, I'm done. Thank you very much.
Thank you very much.